have, let me start with definitions, which I think I have to do. So by an embedding, I will mean a topological embedding today. So for our purposes, when the domain is compact, it is an injective continuous map. Okay, isotopy will be homotopy through embeddings.
Lost video.
Huh? Is everything all right?
Oh. Now it's okay.
Uh-huh.
Now it's okay.
Can you see what I write?
Yes.
Uh-huh. All right, thanks. Well, okay, a link today will be an embedding of the disjoint union of finite Riemannian copies of S1 into S3. Link, so this is link. And a node is a one component link. So just one S1. So I think everything is defined now. Any questions? So then there is the problem of Rolfson. Is every node isotopic to the unknode. So I think everyone knows what an unknode is. It's just this standard circle in S3, equatorial, say. And yeah, all terms are defined here. So I have to say, remark that this problem only makes sense for wild nodes, because all tame nodes, such as smooth or piecewise linear, for example, they are always isotopic to the unknode. So the reason for this, well, let me do it as a lemma. So if we have a node K in S3, well, officially nodes are embeddings. So officially they are maps, but I will also identify nodes with their images, which is an abuse of notation, but it's easier to follow this sometimes. So we have a node K, then we write it like this, and we have a disk, two disks in S3, such that this disk intersects the node in a single point, and it locally separates K. So the meaning is that it is not this picture, but it is some kind of this picture. So officially locally separates means that if we take a small sphere, around this point, a small ball around this point, then and look at its intersection with this node, then it has two parts. these two parts are separated by the disk. And well, what should I say? No, we should remove the disk from, or just this point. We should remove it from this arc, and then no. What is locally separates?
Ну, получится этой частью сферы, и узел должен в обоих.
Нет, по-моему, это понятно. Может быть, на английском трудно переводить.
Okay, I got confused with this. Okay, does anybody want the details of what it means to locally separate? No, then I continue. All right. So under this hypothesis, K is isotopic to the unknown.
Существует P или любого P?
Yes, there exists a disk. So we are given a knot such that it pierces some disk, so to say. So it intersects it at one point and locally separates it. So then K is isotopic to the unknown.
А P должен быть гладкий, D.
Yes, very good question. Thank you. So as written here, it is actually a not so easy theorem, which I think was proved by Rick Ansel not so long time ago. So what I want is something easier. So I want this D to be piecewise linear, or yes, smooth will also do, as you prefer.
А узел у нас не дает гладкое положение.
Yes, the knot can be arbitrary. But if the knot is smooth or piecewise linear, then such a disk always exists. Obviously, yes. Because we just take, for example, if it is smooth, we take any point on it, and then there is a small normal plane, a small normal disk, which is just what we want. Okay, so I'm proving the lemma. Okay. So to prove this, I want to identify the pair consisting of S3 and this disk as the quotient of the following pair: S3 ball, comma the boundary of the 3 ball, modular identification. Let me draw a picture. So this is the 3 ball, and I want the following map row. So it is from. So this ball is the unit ball given by the unit ball about the origin. So this row will be a homeomorphism of the boundary, which is just a reflection. So x, y, z goes to minus x, y, z. Reflection about this plane, vertical plane. And we take the quotient of this pair by this row. So maybe I should write it inside here, B3 modular row and the boundary modular row. But I'm restricting this row to the boundary. I'm only identifying points on the boundary. So I'm claiming there is always such a homeomorphism. And I think this is clear, because after we do this identification, then what remains of this boundary is just a disk. Because we had the sphere and now we have a hemisphere. The sphere identified to the hemisphere. But if we have an arbitrary piecewise linear or smooth disk, it is isotopic to this hemisphere. So we can identify the pair consisting of S3 and this disk with this pair which we have after the identification. So here in
Я не совсем понял. S3 запятая D2 это сфера с маленьким диском. Это значит просто пара многообразий. Ну а можно на картинке нарисовать, как она выглядит?
So the sphere together with the disk looks like this. Well, this is schematic picture, a sphere and a small disk inside.
Да. Ну,
And another instance of this picture is this. Also, well, after I do this identification on the boundary of the three ball, we get a sphere, yes?
Нет, получится диск, потому что если ρ так написать, как по формуле, то x равно нулю переходит в себя. Гиперплоскость x равно нулю, YZ переходит
So
в
rho is
только на границе.
is defined only on the boundary, yes.
Только на границе. Хорошо, ну тогда да.
So it is the identification of this disk by the self-homeomorphism of the boundary. So then you agree, yes?
Ну, если только на границе, то тогда действительно получится сфера. А диск, этот самый D2, где тут получится?
So if we look only at the boundary and take the quotient of the boundary by this row, this will be a disk. Yes? And this pair is standard, so we have a homeomorphism with the standard pair. So we also have a node K here in the sphere, and we can look at its image under this homeomorphism. This will now be some arc. Well, okay, here it will be a node, but we also have the map from B3, partial B3. And we can look at the preimage of K. Let us call it K hat. This K hat, maybe I should call it J. Let me call it J. This J will be an arc. And it will look like this. So originally we had a node which was pierced by a disk. Now we cut it by this disk, and what remains is a three ball essentially. So we take a map from the three balls into here, into the three sphere, which sends this hemisphere homeomorphically onto this disk, and this hemisphere homeomorphically on this disk. But for example, this inside part of the ball goes somewhere here, and this inside part of the ball goes somewhere here. Okay?
4 points in the boundary separate.
Yes. So for this point we have two preimages. And for all other points of the node, we have just one preimage for each. All right. And now in this picture, I'm just doing something stupid. So I look at this, I'm taking the homothety, or dilation, how it's called. So whatever I had, I will do of smaller size, and so I have this ball here, which is like t times b3. So here is somewhere the center, and I'm squeezing this ball by commutating. Okay, but also I'm attaching this to straight line arcs. Yes, so here I can assume that these 2 points are like opposite points of the ball, and also they lie on the x-axis. And here is a small copy of this ball and two straight line segments. So in the end, we will get just one straight line segment, and this whole ball will degenerate into 1 point. This t times b3, I can call it 0 times b3. Here. So we have such a homotopy actually, or actually it is an isotopy of this arc. And if we take its image under this quotient map, so this is quotient by rho, then we get an isotopy of this node here, and it just makes this node straight, so that in the end we get the unknown. Okay? So this is an accurate proof of something that was obvious anyway.
Почему нельзя было сразу сказать, раз внутри там узел такой, что он там локально линия, там где-то далеко за узлом, но его там диск.
Нужно вот он раздвинется.
I did just like that, but I wanted to do it formally because I will use this construction as soon. Okay, any
Good
questions?
Good, great. Can I ask you a question?
Yes?
Yeah, it looks like your sphere pierces the arc at the the 2 endpoints. They're a single point, but also that disk in the center pierces the arc.
Here you mean? What do you mean?
At the endpoints of the arc in that picture you just pointed to,
Yes.
the sphere is piercing the arc, sort of.
Yes.
It's also piercing it in the center, and it looks like it's piercing it in 2 points.
What do you mean in the center? It's piercing it at these 2 points, but I don't know anything about what happens inside.
You don't need to know that. That's not part of it.
Yeah. I don't need to know that. So this piercing results from the original piercing which we have by the hypothesis.
Yeah.
And then we just squeeze this ball regardless of what is inside of it. Okay?
Yeah. Okay.
Okay. So now let me move on.
Gregory?
Huh? Question?
Yes, let's have a remark, because you had said at the beginning the disk has locally to separate the knot. And I think what you are actually, so locally separating is, in my opinion, defined as follows. If you have a sufficiently small neighborhood of an intersection point, and take out the points from the disk, the neighborhood falls apart. And what you are actually using, and I think in this lemma, is a bit more that it locally separates, namely that the knot behaves that it has an interval on one side, takes 1 point on the disk, and all remaining points are on the other side.
Well,
so I define.
I'm assuming that the disk meets the knot in a single point.
Okay. Okay. If you're sorry, I cannot read everything that you write. It's very small on my screen. But if you're explaining this, it's correct.
Okay, I will try to write in bigger letters.
Okay.
Yeah, so you're right. Local separation should be defined like this. The disk locally separates S3 into two regions, and our knot must belong to just one of these regions. So this is local separation.
And it has to meet in one point, okay?
Yes, in one point. I'm
But I
assuming,
believe that.
I'm assuming that in one point. Okay, so there is Rolfson's problem. Now there are some results. So the Rolfson's problem is still open. But what is known is that there exists a link, two-component link of, okay, I should write in larger letters, of linking number equal to 0 and also of linking number equal to 1. So two different links, which is not isotopic to any piecewise linear link. Or if you wish, you can say to any smooth link.
А для других коэффициентов зацепления?
You can do it, but it's not very interesting, I think. Yes. Well, these are two quite different examples. I don't have examples for linking number 5, but it's not a problem to do it. And so I think I covered this theorem in a number of previous talks. I think there are talks in Russian which cover all of it, and talks in English which cover all of it. And of course it is, yes, the linking number 0 part is published. Everything is written up what I'm going to tell today.
Я помню, вы взяли вариант Сателлевина и иррациональную дробь.
So this is proved just by using Cochrane's invariants, and this is proved by using their generalizations to links of linking number 1, and this generalization is found in the two-variable convex polynomial.
Are there one wild point in those examples, or more? Could you remind?
In this example, there is just one wild point, and in this example, there are the whole first component consists of wild points. It's a Binks link.
All points are valid.
Yes, for one component, but the other component is tame in both examples. So I regard this as known, and I hope that in future talks I will prove stronger results. But now, yes, there is another theorem which says that the Binks link, yes, well, I don't know. The Binks link is a certain wild knot. Let me not draw it now to save some time. The Binks link, or you can read it as a certain wild knot if you don't know what it is not isotopic to the I knot by any isotopy which extends to an isotopy of a two-component link with linking number 1. So if I insert an additional component to this Bing's link in any way so that the linking number is 1, then this link, this component link is not, well, actually it's not as isotopic to any piecewise linear link. Yes, and this is also true. And I think I also this was also proved in my talks in September, which were in Russian, and in my talk in the Polish Academy of Sciences, which was in English. I think I did give a sketch of proof of this there. So I regard this as known also. So then the question arises, if every isotopy of a knot always extends to an isotopy of two-component link with linking number 1. If it always extends, then the Rolson problem will be solved using this theorem. But unfortunately the answer is negative, and this is a theorem of Andreas Zastrov. So not, well, there exists an isotopy from the unknot knot to itself, which does not extend as above. So it does not extend to an isotopy of a two-component link with linking number 1. So like here. Okay? Well, Andreas had a different statement, slightly different statement, but this follows from his construction, and I think I'm going to explain this now.
Ну там большая, наверное, все умеют теорему доказывать. Что касается меня, то я ни первую, ни вторую, ни третью не умею доказывать. Я просто свой статус слушателя хочу объяснить. Так что, видимо, что дальше будет совсем уже это самое круто. Ну, я какие-то обрывочные представления имею о том, как доказывается.
Петр Михайлович, all these theorems...
Пожалуй, я знаю, потому что вы первую рассказали, а вот вторую и третью...
Вторую тоже рассказал.
Ну, может быть, вторую вы рассказали,
а третью сейчас...
Я уже не слушаю.
All these theorems are non-trivial, and yes. So the second, yes. Okay. Well. Okay. So I understand. So that some people missed my previous talks, but I hope that in subsequent talks I will prove these theorems again. Okay. And today let us focus. Well, not for the whole time today, but in the beginning, let us focus on the theorem of Zastrov. So I'm going to prove this because what follows will be based on this theorem. And before I state additional results, let me prove Zastrov's theorem. So we need to start from the Alexander sphere, the Corinth sphere of Alexander. I had a picture somewhere. So this is this is the picture of Alexander's horn sphere. We start from a torus, but without a cylinder. How should I draw it? Then, well, we can draw disks here, but remove smaller disks, and then to the smaller disks we attach handles. I should draw it. These handles are going to be linked. But now we again remove some cylinders from these handles. And we continue in the same fashion. So there will be two linked handles here and two linked handles here. And then we again remove some cylinders and so on. So the result of this is a wild sphere. I mean, I would have to say more details if you have never seen this picture, but probably everyone knows this, yes? Huh? Good. Yes, so this is Alexander's wild sphere. Now there is Rollson's wild knot, which is, well, if I draw it in a nice smooth way like this, then this wild knot will be just the visible outline of this picture, contour. So let me do it. So I do something. Well, let me draw in stages. So if I draw it in stages, then I would just draw like this, but this has to link another one. Okay, but now I remove something here and something here, and then I will again have something complicated here. Let me not draw the details. Well, it is not in the plane because here there is linking.
Yes.
Yes. So it's. So should I explain it in more detail or this is clear? Okay. So there are in most pictures we can draw some balls. So there is a first ball which contains everything, and then there are two balls in the next stage which contain this stuff. Let me call them together B1. And then we have Bn, which consists of 4 balls. So in the intersection of these balls Bn from n equals 0 to infinity is a copy of the counter set. So this counter set is a set of wild points of this sphere. And we have the similar situation here. We have this balls here, which is B1, and this ball B0, and so on. And actually we can identify this Rolfson's wild knot with the equator of this Alexander sphere. So it's, well, it's I can draw it somewhere here, or just regard it as a visible outline. And then these balls are just the same as those balls. So now the construction of Andreas is as follows. So he starts with Rolfson's wild knot, and he looks at two meridians. Let me call them J1 and J2. So they bound disks which intersect this wild knot in a single point. And then, using the lemma which I proved in the beginning, starting from each of these disks, there is an isotopy from Rolfson's wild knot to the unknot. So we have two isotopies to the unknot. This corresponds to, well, maybe I should call this disk D1, and this disk is D2. So this isotopy corresponds to the disk D1, and there is another one which corresponds to the disk D2. But now I can pass the first isotopy in the opposite direction, and I obtain an isotopy from the unknot to itself. So the claim is that this isotopy from the unknot to itself doesn't extend to an isotopy of a two-component link with linking number 1.
Простите, имеется в виду некоторое конкретное зацепление, или если любую такую компоненту добавить, то не будет продолжаться?
So it doesn't extend to any two component. No matter how I insert the second component, as long as it has linking number 1. Yes, I'm clarifying. So I can, yes. For example, both J1 and J2 work. It cannot extend to an isotopy which at this level is either J1 or J2, or you can draw some other.
Ну, для окружности они все одинаковые, так что здесь вопрос не по делу.
Yes, here there is no much difference, and we will use it. So actually, let me prove a stronger assertion. Let me write it down. There. For clarity, so assertion or claim Dastroff's isotopy does not extend to any link homotopy of a two-component link with linking number 1. So what is a link homotopy? It is just a homotopy which keeps distinct components disjoint. And each component can self-intersect itself in any way it wishes.
Простите, а как по-русски я забыл вот линк.
Зацепляющая гомотопия или просто гомотопия? So now there is a lemma. So let us look at this Zastrov isotopy. So let me call it HT, for example. So I can regard HT will be a map from S1 to S3. Okay, but there is also a map H from S1 times I into S3 times I, which is defined by H of xt equals Ht of xt. So let us look at the following set X. It is just a complement in S3 times I, S3 times I. We subtract the image of this H. And the lemma says that X deformation retracts onto S3 times 1/2 minus H 1/2 of S1. So by this I mean Rolson's wild knot. Okay, is the statement clear? So we have this isotopy from the unknot to itself going through Rolson's wild knot, and we consider this isotopy in S3 cross I. So this is S3 cross I. There is a middle section, S3 cross 1/2. And there is a trace of this isotopy. Here is the unknot. Let me use different color. Here is the unknot, here is the unknot, and here is Rolson's wild knot. And there is some, well, okay, let me draw it like this. So there is one arc with this disk D1 and another good arc with this disk D2. This is D1, this is D2. So corresponding to D1 we have an isotopy which shrinks all this stuff to a point. And corresponding to D2 we have an isotopy which shrinks all this stuff to a point here. So we have this isotopy, and the claim is that the complement to this isotopy deformation retracts to the complement to Rolson's wild knot.
The complement of what?
The complement of the isotopy deformation retracts onto the complement of Rolson's wild knot. Okay?
Не, ну, образ H это все S3 умножить на 1, на S1.
No.
А, S1, я понял.
This is S1. This is isotopy. The complement to the isotopy, deformation retracts onto this complement. So to prove this, it suffices to show that this lower half deformation retracts onto this complement and the upper half. So we can consider the two parts separately. In each part, we have this isotopia which comes from this picture. So we actually want to construct a deformation retraction of this picture from bottom to top, of the complement to this isotopia of the arc onto the complement to this arc. And yes, we want to do it carefully enough so that it is equivariant on the boundary, because we want to identify the boundary later. So we want this deformation retraction to be equivariant on the boundary with respect to mirror symmetry. Okay?
А чем будет? Там вот в середине S3, нет, вот вторая строчка снизу, x, нет, я формулу смотрю, S3 умножить на i минус h на S1 минус i. Это оранжевая, что ли? X
это оранжевая, это изотопия.
Значит, h это оранжевая. Я должен выкинуть оранжевую, да? Дополнение к оранжевой деформируется на что? На среднее сечение, дополнение к оранжевой.
Достаточно проверить внизу и вверху отдельно. Внизу и вверху вот такая картинка.
Ну, если в конструкции будет в раздельности деформация, то можно проверить в раздельности.
The middle section is anyway, it's a strong deformation retraction, so it keeps the middle section. It doesn't move the middle section. So then, yes, I should say strong deformation retraction. Okay. So we want to construct a deformation retraction of the complement to this isotopia of the arc onto the complement just to this arc in the top slice. And I think it's quite easy to imagine it, because it just goes well, if we have any point at any level, so there is the center of this ball. So this picture is all these balls are round and centered at the origin. So we can look at the ray coming from the origin and going through this point, and we move our point along this ray until it reaches the boundary, well, we should be accurate with which we should be accurate to determine the speed with which it moves, because we want the points here to move so that they, if they were in the complement of the knot, then they will remain in the complement of the knot all the time. So we just, but it is possible to do this, because this was the squeezing of this ball, gradual squeezing of this ball, and we can unsqueeze it now. But the points which are outside this ball will of course be bumped into the boundary of the original ball, and the points which are inside some green ball will always keep inside the green ball, and here they will not go to the boundary. So this is the idea, and there is a formula. So do you want me to write the formula actually? Yes, Andreas говорит, Andreas says he wants, yes.
Я вот не понял смысл леммы, это для всех узлов так выполнено или для каких-то особых?
So the lemma, it's a good question, because here we are not using much from this construction. The lemma applies to an isotopia of the following type. It is an isotopia from the unknot to itself, which is constructed in the following fashion. We start from some wild knot, not necessarily Rosen's wild knot. We start from some wild knot which has two meridians. So that we can draw two disks which intersected in one point and locally separate. So if we found such a wild knot which has two such disks, then we can construct two isotopies to the unknot. And then we get an isotopy from the unknot to itself. And for isotopies from the unknot to itself of this type, we have this lemma. That the complement to the isotopy, the formation retracts onto the complement to the knot.
Ну, то есть, если вот, понятно, что сама эта ретракция, эта самая изотопия, она тоже стягивается на центр. Ну, просто по определению, как бы, да?
Okay, you can say so. Yes.
Ну, и то есть можно придумать контрпример, когда вообще говоря, это...
Well, no. I think there is some problem here because so Nikita says that the isotopy itself also can be constructed. Well, this is not so easy because in the last moment, in the very bottom stage, we have this point 0, and this point 0 we cannot apply this construct. There is nowhere where we can move it. It stays on the knot, but if we wanted to stay on the knot, we may have difficulty. So we are looking at the complement.
Ну а вот когда вот Никита возразил по поводу точки, а почему здесь эта ретракция в окрестности точки идет? Куда она девается? Вот надо поставить ретракцию, и вот все в точку прошло. Что в начальный момент происходит в этой точке? Можно прояснить на пальце?
Nothing happens at this point in the beginning, because we are looking at the complement of the knot, or of the isotopy, and this point is not in the complement. So this point is also not in the complement, and we don't have to do anything with it. But for this point, we have to do something with it. And namely, we will do the following. We will move it along this ray until it reaches the boundary.
Ну, а вот когда мы немножко туда вклеим, то что получится? Так же по получу нельзя уже будет пойти?
Можно. We do the same thing here. We move all points along the corresponding ray. The question is with what speed we should move them. This is the only question. And I can write a formula, because Andreas asks me to write a formula, I will do it.
А там не будут накладки вдоль этих лучей? Вот вы сейчас формулу выпишите и не будет накладок, да? Просто тень будет пересекаться. Если бы там все лучи были бы, ну, узел виден с пересечениями вдоль лучей.
Yeah, I'm sorry to Rick, because I was hoping that we'll finish this at least by 6, but with formula probably there are no chances.
Нюансов, конечно, хочет формулу, может он заранее все это заказал, но пока что он ее не просил.
Этот вопрос можно потом.
Может не будет формулы?
No, Andreas wants, the author of this theorem wants to see the formula. So, the formula is as follows. RT of V, it's not complicated.
В первый момент он это выталкивает, а потом появляется заузленность. И вот он не должен там зацепиться, да? Вдоль луча.
Неустранимым образом пересечение будет.
Ну, если бы там ничего не было, то тогда бы и понятно было бы, что вот в тот момент, когда точка, там ничего не происходит. Там появляются заузленности, и он говорит, что все равно можно когда выдавливать, надо в оранжевую не попасть.
Okay, so this is the formula. Let me explain this formula.
Формулу вряд ли можно прочесть. Это для Ансела формула.
So first, we have to consider this ST, which is linear motion from S to 1. So we have this is a homotopy of 0, 1, and it does the following. If we had so well, it's maybe it should be called HT of S, but I'm calling it as ST. So if we had some point S, then it will move to 1 with linear speed. And you can see it here. When t equals 0, this is S. When t equals 1, this is 1. So this is linear motion from S to t with constant speed. Okay? Now I'm using this ST, and so this is the deformation retraction. So t is the time of the deformation retraction, and S is the level in this picture. But let me see. So in which direction? So we want. Yes, I think in this direction. So this is 0, and this is 1. Yes, this is 0 and this is 1. But I have to write 1 minus S. So actually here S equals 1 and here S equals 0. It's a little complicated. Yes, S equals 0 here, S equals 1 here. But you see, anyway, I subtract 1 minus ST, so this cannot be simplified. So we had our point, which was at some level. So we had some S. So here is we start from 0, go up, and there is some level corresponding to S. So then this S will if you look here, this S will be replaced by ST, and ST just moves S to 1 with constant speed, and S equals 1 is here. So it means that our deformation retraction takes any point at any level and always moves it up with constant speed. So far it's just the second coordinate. I mean, it doesn't move it down or it doesn't keep it at the same level. It moves it to upper levels with constant speed. Now what happens in the horizontal direction? In the horizontal direction, so we have this V here, I treat it as a vector. So this is a Euclidean 3 space, round ball, and this is the origin. So this is the vector V, and we can scale it. And this is the scaling of this vector V. So from this you can see that we always stay on the same ray. And now what are we doing? Here we multiply V by ST divided by S. So ST is something which can be only larger than S. So this is always greater than 1, or it can be equal to 1. So this means that we upscale this vector, it becomes longer and longer. But if it becomes too long, if it becomes longer, then it's longer than 1 over the norm of v. Then we stop upscaling it. Because we don't want its norm to become greater than 1. 1 is the radius of this ball.
Мы это применяем только к черным точкам, к оранжевым не применяем.
Yes.
И утверждается, что мы на оранжевое никогда не попадем.
Yes.
Если мы...
Yes.
Ну а как же так? Мы можем залезть на оранжевое.
The orange points are obtained from this construction, and this construction squeezes the ball together with orange points. So inside of this green ball, we are just doing the same squeezing which was originally, but in the opposite direction. And
А где можно, там получится.
yes, and outside we have to do something. So we just keep going until we get to the ball.
Ну, в общем, наверное, правильно.
The only unobvious thing is really at this point 0, because as you remarked, we cannot extend this this deformation retraction to this point 0, but we don't have to do it because we are doing it only for the complement. So we can extend it to orange points for s greater than 0, for all levels above the 0 level. But at the bottom level, we really have to remove this orange points. Okay? Any questions?
Матросов нет вопросов. Как вы переведите американскому другу? Он, небось, по-русски понимает ансамбль. То есть можно это самое его разыгрывать, да?
Okay, so if there are no questions, I'm assuming that we are okay with this lemma, and I continue. So now we want to prove the claim that this isotopy doesn't extend to any link homotopy of a two-component link with link number 1. So assume that it does. Assume that we have we are able to insert the second component. So it can be any component, just it has to have link number 1. And then there is some link homotopy. So it can have self-intersections, but it always stays in the complement of the white component.
В общем, они не гомотопны в этой картинке друг другу никак, а должны быть гомотопны, да, потому что мы их туда запихнем.
Yes, but let me say it in detail, okay? So first, let me choose the meridians here, and let me observe that whatever this node was, it is homotopic to this meridian in the complement to the unknown. Because the linking number is the same and this is the unknown. So I can assume that we actually start from this meridian and end at this meridian. Now, and yes, and so this is not just some arbitrary meridian. This will be J1, which was here. So recall that this isotopy was based on this disk D1. So actually this disk D1 and yes, nothing happened with this disk D1, but something happened with its complement. Its complement was shrunk to a point. But J1, it still exists. So in this isotopy, nothing touched this J1. Maybe I should draw it in blue. And draw this cylinder. And this cylinder is still in the complement to the isotopy. And similarly here. But this is J2. So now we have the following homotopy in the complement. So we have this complement X, which is S3 cross I minus H of S1 cross I. In X, we have the following homotopy. It starts from J1, then goes to this meridian, then goes by the given link homotopy somewhere here. There is something unknown here, which just has linking number 1 with this white knot. And then it goes with the given link homotopy here, then to this meridian J2, and then back to this J2. Okay, so there is such a homotopy which starts from J1 and ends at J2. Now I apply the deformation retraction which we constructed and apply it to this homotopy. And so we get some homotopy from J1 to J2 just in the complement to the white knot.
Простите, вот мы распутыванием перешли от J1, вот, допустим, туда, а следующий шаг как?
So this green part is the link homotopy whose existence we assumed. So we are proving that there exists no that this isotopy doesn't extend to a link homotopy of a two-component link, and this is, and I said suppose it exists, and then this is its picture. Okay, so we have a homotopy from J1 to J2 just in the complement to Rolfson's wild knot, and we want to get the contradiction.
Я логику потерял. Значит, мы доказали эту лемму, а почему не существует? Мы стерли.
We proved the lemma about the deformation retraction.
Да, и она помогла доказать, что
Yes.
нету чего, повторите?
The proof is not finished yet. So the proof is reduced to a simple assertion. So the claim we are proving is the following: that the given isotopy, Zastrov's isotopy, does not extend to any link homotopy of a two-component link with linking number 1. Okay, this is what we are proving. This is our aim. So suppose it extends. So then I'm drawing this picture of this link homotopy which is given on the second component. Then I can replace this beginning of this link homotopy with the meridian and this end with the meridian. But I'm choosing these meridians specially so that they're the same as this J1 and this J2. And then there is also a homotopy here from J1 to J1. I'm just leaving it at the same place. I'm not moving it anywhere, but this does not intersect the white isotopy. And this one doesn't intersect. So now we have a homotopy from J1 to J2 in the complement to the white homotopy. Now I'm applying the deformation retraction. And I'm obtaining a homotopy from J1 to J2 just in the complement to Rolfson's wild knot. So what remains to be proved is that J1 is not homotopic to J2 in the complement to Rolfson's wild knot. Once we prove this, we are finished. Okay.
Where here link with linking number 1? It's white with green or white with blue?
White with green and white with blue also.
Почему два каких-то случая?
So the green part is what we are given by hypothesis, by proving by contradiction. And the blue part is given just from the picture, because here we draw this J1 and here we draw the same J1, and we notice that this J1 does not intersect the white isotopy at any moment. So then we can first go blue and then go green and then again go blue. And this is a homotopy from J1 to J2 in the complement to the entire isotopy. But using the deformation attraction, we get a homotopy from J1 to J2 just in this middle. Okay? So what remains to be proved is just that J1 and J2 are not homotopic in the complement to Rolson-Swell knot. And this is a matter of, it can be called an exercise maybe, but let me prove it. So suppose that there exists an isotopy, a homotopy. I need some new color, red. So suppose that there exists this homotopy in the complement to Rolson-Swell knot. Then this homotopy is disjoint from some BI. Well, it is certainly disjoint from the counter set, because this counter set sits on our wild knot. And then it is disjoint from some neighborhood of this counter set, but this means that it is disjoint from some BI. So we have the following. J1 is homotopic to J2 in S3 minus, well, yes, this was called H1 half of S1. Let me call it K, or maybe R. Rolson-Swell knot. R for Rolson. So S3 minus R and union with some Bn. So there exists an N such that J1 is homotopic to J2 in this complement union with some ball. Okay? Now I want to look at this picture also, and
Но когда вы так сделаете, то вы там уже фундаментальную группу можете посчитать и не получится.
Ну, я это и собираюсь сделать. So here, this is Alexander's wild sphere, and also there is Alexander's wild ball, which is inside the interior part. But I can do a hole here. So I'm removing a cylinder from this ball, and this will be a solid torus. Well, maybe I don't know how to draw. Yes, so I'm removing a handle. This handle can be called H.
Как мы G1 и G2 загнали в BN?
So the homotopy from J1 to J2 does not intersect the counter set, because the counter set sits in the Rolson-Swell knot, and therefore it also doesn't intersect some BN.
Не пересекается.
Yes.
Да. Там дополнение говорит.
Yes, yes, thank you.
Это without.
Without being, yes, without being. But I want to construct a deformation retraction onto this from, so let me call this Alexander's wild bull somehow. How can I call it? A. So I have also S3 minus A and minus H and minus Bn. And I think there is such a deformation retraction.
Это что такое?
Шарик какой-то.
Не нарисовано.
A is Alexander's bull, Alexander's horn bull.
Что это такое?
Но рогатый шар, внутренность рогатой сферы. Okay, let me write in the way it was written, so I can remove this union. This is the same what was before. And I can write okay, the claim is first the claim is the following. If I just look at R union with Bm and I look at A union Bm but minus H, and this deformation retracts onto this. This bull without the hand, Alexander's horn bull without the handle, but with some Bn added. The formation retracts onto this knot with some Bn added. So then I claim that the fundamental loop of this is the same as the fundamental group of the complement to this. Yes. So the fundamental group that we are interested in, the complement of the knot and to some Bn, is the same as the fundamental group of the complement to the Alexander bull together with Bn but without the handle. I think it is clear.
По-русски можно? Значит, из Александровского шара это обычный шар, да? Он
рогатый шар.
Он это самое. Я просто не знаю. Это не гомеоморфно обычному.
Нет, он гомеоморфен обычному шару, но он дико вложен. Дико вложен, да. Дополнение не гомеоморфно.
Нет, но мы из шара вырезаем ручку.
Да.
Но я знаю, что получится. Если из шара вырезать ручку,
Получится полноторик, да.
да, получится полноторик.
Но еще,
утверждается,
но еще мы добавляем здесь BN какой-то, то есть некоторое количество шаров.
Ну хорошо, допустим...
Вот, утверждается, что дополнение к этому имеет такую же фундаментальную группу, как дополнение к этому белому узлу вместе с каким-то BN.
Ну, наверное. Сейчас, а как эта ручка аж там? Потому что... потому что она туда уходит, что ли?
We don't have this, anything here, so there is empty space here, and this is where we remove this handle. We can make this handle wider and wider until we remove all this stuff which is here and which is here. And...
Хорошо.
Можно вопрос? А можно левую картинку рассматривать как правую? Мы вырезали шар из этого, из границы, и получилась вот эта вот ленточка, которая слева, или это неверно?
Левую рассматривать чего?
Если рассмотреть как ленточку. Левую картинку.
Вы про вот это вот?
Да.
Ну, это гомотопия, да. Ну, образ ленточки, ну и что?
Но если с правой картинки вырезать из границы сферы маленький шарик, то она не будет гомеоморфна этой вот ленточки. Ну, ладно.
Ну, что-то я не очень понимаю.
Мы хотим показать, что G1 и G2 не гомотопные. Для этого мы делаем модель, и вот я так понимаю, что мы будем рассматривать вот там, да, вот в этом правой картинке.
We want to prove that J1 is not homotopic J2 in the complement to Rolson's wild knot. We can add some BN to get rid of this wild part, actually, to simplify things. And then we want to modify it a little bit more, so we want to compute this fundamental group. Yes, a complement to Rolson's wild knot and to some BN. And I'm just saying that it can be computed, it is isomorphic to some other fundamental group. Namely, we can look at the whole Alexander's ball instead of Rolson's wild knot, but remove a handle. Okay? And it is the same fundamental group. Just because we can make this handle bigger and bigger, and then we eventually get...
Какая же там группа, можно сказать?
Yes, I will say in a moment. Is it okay, or it needs to be discussed?
Не, если вы напишете, какая группа, то мы сразу поймем, что она общая для правого и левого рисунка, а так абстрактно вы можете дольше объяснять.
So the reason why I need this is because I really want to look at this removed handle. So this removed handle, so I want to apply Seifert-van Kampen theorem. And it tells me that the fundamental group of this complement is the free product of Z, which is generated by this loop going around the handle, and the fundamental group of this complement, but without removing the handle. Let me write it. So this is the free product of Z and the fundamental group of this complement, but without removing the handle.
Ну, теперь рассказывайте, как G1 зацепился за ту дрянь.
So when I'm removing this handle, I'm adding a free factor Z. This is the claim. Okay? Ударение ручки соответствует добавлению свободного слагаемого Z. This is what is written here. And finally we can compute something. So we have J1 and J2, they sit in this group. So let me call G1, let me call it M. I need to fix a base point somewhere. So maybe I fix it here, and I call this base loop no, I call this base loop X. But also I want to look at another loop. I want to look at another loop, namely this loop. In this picture, it is a meridian of this solid torus. And I call this M. So there are some orientations. For example, it can be like this. And yes, I want to add some tail here. But if I add it like this, then so J1 is X, but J2 will be, well, maybe I should. Yes, I think it should go look in the opposite direction because here it comes this way, yes. So and then this should also look in the opposite direction. And then I can write that J2 is Mx, or maybe Xm. Xm.
Как это MX? M это петля или что это такое? M это число?
M is this meridian, the meridian of the solid torus.
Что такое XM?
Product in the fundamental group, yes. Because, so what is Xm? X is this. We first go here and then we go here. But you can see that it is the same as just to go, yes, the different tail. The tail should be like this. If I go like this and then like this, it's the same if I go here, 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 and here. Okay? So, in this fundamental group I have X and Mx. And I want to prove that they are not conjugate. Now, so what it means that they are conjugate? It means that Xm equals J inverse Xj for some element J.
Классы сопряженности, они образуют множество изоморфных Z, да?
Нет, там сложно.
Нет, это сложно.
А почему-то нужно доказать, почему этого хватит, если... все, простите.
We want to prove that these two loops are not freely homotopic. Without freely means not remembering the base point. And free homotopia corresponds to conjugacy in conjugacy class in the fundamental group. Okay. So this equation can be rewritten as follows: M equals X inverse J inverse Xj. So this is the commutator. M equals the commutator Xj. And I claim that this is not possible. There does not exist any J such that this equation is satisfied. Why? Because we have this free product, and there is a normal form for elements of free products. So it's like the structure of the free group. So what is an arbitrary element of such a free product has a unique expression in the following form. We first take some element of, for example, this factor, then some element from this factor, then from this, and so on, and we write such a word, and we stop, and that's it. Maybe I should write it. Every element J of a free product of two groups G star H can be uniquely expressed as G, no, let me call it A and B. G equals A1, B1, AN, BN, or, so this is or, G equals A1, B1, so on, AN, BN, AN plus 1, or G equals B1, A2, or I don't know, A1, so on, BN, AN, or G equals B1, A1, so on, BN, AN, BN plus 1. So every element can be expressed in one of these four forms, and such an expression is unique. So we have the following situation. M belongs to this factor. X belongs to this factor. And G, we don't know where it belongs. I actually had a mistake in my text. We don't know where G belongs. But no matter where G belongs, it can be expressed in this way. And then what can happen? So we have to substitute this expression, for example, the first expression here and here. So let me, for example, take this first expression. So then we get M equals X inverse A1, B1, so on, AN, BN, then X, inverse, sorry, and then A1, B1, AN, BN.
Кажется, можно быстрее. Если профакторизовать по одному из слагаемых, то получится, что элемент во втором слагаемом сопряжен единицей.
Okay, maybe you are right, yes. If we take the quotient by this z, then this x disappears, so j and j inverse cancel out, and we get that m is trivial in the quotient by z. But then m is trivial, m is just trivial, yes, so you're right, we have proved that m equals 1. This is good. And if we take the quotient by this, then we yes, I think actually this is enough. This is enough because m, we proved that m equals 1, but m is not equal to 1. M is this meridian of this Alexander horn ball. And here I'm not removing the handle, so I can forget about this handle now. It is just the picture of the Alexander horn ball, and we take this loop. And because people have studied the Alexander horn ball for many years, they have proved that such a loop is not homotopic to its trivial loop.
В общем, это народная теорема.
So I have a reference to Fox. Fox computed the fundamental group here. And
но кажется, если сказать, что x равен единице, это еще проще, потому что он образующий свободным слагаемым, он просто в z единица не сопряжена нулю.
Я по-моему, это и сказал, нет?
Мы сейчас про m говорили.
Про m мы ссылались куда-то, а для x совсем...
No, but you cannot prove, you cannot directly prove that x equals 1, can you?
Ну, профакторизуем вот свободное произведение по второму слагаемому.
Okay, then this disappears, But here, what
0 сопряжен единице z.
Не, ну G не лежит во втором слагаемом.
why? No.
Фактор это гомоморфизм.
Нет, ну, если мы будем уже представлять из этих формул, то как вы говорите, получится, да.
No. This just implies that G lies. No, this doesn't imply anything. X is conjugate to itself.
А почему слева будет 0 z, а справа будет... Ой, да, простите.
Нет, ну если же поставить из этих формул...
We started by assuming that X is conjugate to MX. If we kill M, then X is conjugate to X. Yes, Петр Михайлович?
Нет, ну вроде это самое, народ доказал, я думаю, что...
Yes, this is just direct computation, and we don't have to do it because it was done. Okay?
Ну да.
So I think Zastrov's theorem is proved now.
Мне кажется, да. Вот, но он мог бы и попроще взять зацепление, там можно было бы, вот как Никита сказал, произвольное зацепление дикое, без этих самых, без таких сложных вычислений. Там бы тоже получилось бы. Он просто хотел еще именно Рольфсон. Вот ему нравилось, что Рольфсон.
I think that if you take any other, if you take some more usual while not instead of Rolfson's while not, the proof will be more difficult.
Почему?
Because of experience.
Нет, ну как, он вот эту лемму только алгебраически должен был доказать, но она...
I think that this was a very simple argument. It's just several lines. If you take some more usual while not, you will have to compute its fundamental
Ну, хорошо, я понял. Аргумент понятен, ну, наверное, так и есть. Хорошо. Понятно.
Misha, questions? No? Any other questions?
А можно еще раз повторить? Вот мы доказываем, что два синих узла не гомотопны. И как мы с правой картинки переходим?
So to prove that these two loops are not freely homotopic is the same as to prove that the corresponding based loops are not conjugate in the fundamental group of the complement. So I mean the complement to this white curve, Rolfson's wild knot. And we can also take the complement to some Bn. But then, so we just have two specific elements in this fundamental group. Sorry, I erased. It was here. It was here.
Еще нету вообще.
Yes, it was here. But it is isomorphic to this fundamental group, which comes from this picture. So I just I can draw this Alexander's ball. I can drill a hole in it, and then I make this hole wider and wider and wider. So it gets also closer here, and then out of the Alexander ball, only this boundary remains, this visible outline. От рогатого шара остается только его контур. Если мы растягиваем эту ручку, она вот все это черное пространство поедает постепенно, залезает во все эти дыры и пролезает всюду, кроме вот самого краешка картинки.
Ну, понятно.
А там как раз наш узел.
Все ясно. И вот это M, это там сумма произведения этих двух синих петель, как бы, да?
Ну да.
Да. Все понятно.
All right, so maybe I now state some results, and then I think it's time to have a break. Yes?
Первый, да?
But maybe
Я это самое, что...
before the break, can I state some results? Because yes, so the question now, what to do? So what to do about Rolfson's problem? So there was the theorem that the Bing's link is not isotopic to the unknown by any isotopy which extends to an isotopy of a two-component link with link number 1. Even I can prove that the Bing's link is not isotopic to the unknown by any isotopy which extends to a link homotopy of a two-component link with link number 1. But not every isotopy extends to such a link homotopy. Here is a counterexample. So what can we do?
Я не помню в конце. Не любая геометрия.
Не любая изотопия узла продолжается до изотопии или даже гомотопии двухкомпонентного сцепления с коэффициентом сцепления 1.
Ну это мы доказали.
Да, да.
Нет, а потом мы что-то прибавили.
Нет, но еще была теорема, что слинг Бинга не изотопен тривиальному узлу такой изотопии, которая продолжается до такой гомотопии.
Это откуда теорема ваша, что ли?
Ну, моя теорема, да. Но это я в сентябре доказывал, рассказывал.
Да.
Вот, но вопрос, the question is what to do now. How to solve Rolfson's problem, given that we have such an example. Well, my approach is the following. So we want to insert the second component. We definitely want to insert the second component because I want to use some link invariants. I don't have any other approaches which do not use invariants of two-component links. What can we do with the second component? If to change it even by homotopy in the complement to the first component is already not enough. Well, we can change it by Bordism in the complement to the first component. What is... Yes, I will define it now. What does it mean to change by Bordism? Essentially, it means that we replace our second component with another second component, so that they differ by a commutator, for example.
Тогда вот эти вот синие пятна одинаковые будут, да?
Yes, actually, in this picture, an interesting thing about this picture is so we have proved that these two blue loops are not homotopic in the complement to Rolfson's wild knot. But if we allow them to be bordered, of course they are bordered because just here, so they bound a surface in the complement to Rolfson's wild knot. And moreover, they bound a group of any height. So let me define a group.
А какое слово вы сейчас произносили?
Сейчас напишу. Group. Ну, по-русски как-то это не очень переводится. Щуп, может быть.
Это термин или...
Да, термин. So, a group of height 1 is just a surface with boundary. A group of height 2 is a surface with boundary in which we have chosen some generators of homology and we have grouped them by surfaces. Any number of handles you wish. So this is an abstract picture. We take the union of the original surface with these 4 new surfaces along these circles. So we glue these new surfaces to the original surface along these 4 circles. This is a 2-dimensional complex, polyhedron. And this is called a group of height 2. So any number of handles in the original surface and in any of these surfaces. And you can probably imagine what is a group of height 3. To define a group of height 3, I will take also standard basis of homology in all of these surfaces, and again glue them by surfaces. All of them, let me not draw. Okay, so this is group of height n. Is the definition clear? So I claim that these 2 loops, well, actually this orange meridian M, it bounds of a group of any height in the complement, even in the complement to the Alexander ball, and certainly in the complement to Rolson's wild knot. Because you can draw a surface here, and then here you can attach further surfaces. I mean, you get a handle here, but to this handle you attach 1 handle on the inside and 1 handle on the outside, and the handle on the outside will go here, and so on. Is it okay? So what does this mean algebraically? Algebraically, this means that J1 where x is conjugate to mx, or you can write J1 and J2, modulo Jn for any n. So what is Jn? It is a derived series. J0 is J, G. G1 is the commutator subgroup. Or I can also write G prime. G prime. The derived series, it is also called. And Gn plus 1 is the commutator subgroup of Gn. So what is the relation between the derived series and groups? Well, if you choose some base point here, then this loop is homotopic in this surface to the commutator of these 2 loops times the commutator of these 2 loops. Does it need to be explained? Because if you draw a punctured torus, then this boundary of the punctured torus is homotopic to the product of these 2 loops, to the commutator of these 2 loops.
Через развертку, наверное, проще всего.
Yes, yes. Yes, and this cycle is homotopic to this cycle. and any surface is a sum of handles. This is a handle, and so I think you can see that. So the lemma is, if we take the fundamental group of some space, and take its yes, if we take some element of some fundamental group, then G belongs to the nth derived term if and only if G can be represented by a map from gamma to X, where gamma is a group of height n. Well, this is yes. If G belongs to the commutator subgroup, for example, if and only if it extends to a map of a surface bounded by this loop. So this J1 and J2 are conjugate modular any term of the derived series. In this picture.
Группа G там это свободное произведение наше, да?
The fundamental group of the complement to this Rosen-Wild knot, for example. We now forget about this free product, we just look at the complement of Rosen's Wild knot. So if I allow to replace, here I start from the meridian J1, I keep it, then I suddenly replace it by some other curve, but so that J1 and J2 compound a group of some height. And then I keep J2 and I obtain almost homotopy. Almost homotopy in the sense that I allow a finite number of replacements. But for each replacement, these two loops must be conjugate modulo some term of the lower central series. And this will be called n-bordism if I fix the term. So let me write the definition. N-bordism is let me say a sequence. Well, let me draw a picture. It will be too long if I write it. So we have an isotopy on the first component, isotopy, and on the second component we have some number of link homotopies. So intersections are allowed. Link homotopy, and then we suddenly replace this component by another one, and then again do a link homotopy. And then again replace this component by another one. And then do a link homotopy. And so each exchange, so I should call this node somehow. Maybe K1 and K1 prime. And here K2 and K2 prime, and so on. So I'm assuming that each Kn да, спасибо, да. Each Ki is the class of Ki in the fundamental group. Maybe okay. So there is some time. There is time also. So this was K is okay. This is Q Q0, Qt, and this is Qt1. The first moment when we want to do the replacement. So this should be called Kt1, K prime T1, Kt2, K prime T2. Okay, each KTI in the fundamental group of the complement to QTI. Is conjugate to the class of K prime Ti modulo the nth derived term of the nth derived subgroup.
Это вот изотопия двухкомпонентного сцепления, да?
Yes, so I don't know if it is a good name, but I call it an N-boardism. Maybe you can suggest a better name. I'm really interested in isotopies of knots, but the question is, can they extend to something involving two component links? This something is called an N-boardism if these replacements are modulo the nth derived subgroups. Or you can say that these two knots count a group of class n in the complement to this one.
Ну, теперь вопрос про n. Что вы с ним будете делать? Существует n?
Yes, the question is about n. You are absolutely right. For this particular isotopy, let me write it. So Zastrov's isotopy extends to an N-boardism for each n. And now,
Сейчас, что сложнее для больших n построить бордизм? И что из чего следует?
для больших сложнее, потому что вам нужно, чтобы для больших нужно группу продолжать.
А вот как про n-бордизм сказать, он n-бордизм чего? То есть,
Вот эта вторая компонента контролируемая, она дергается.
It's better to say that it's an N-boardism of a two-component link. But the border is important, because on the first component we have isotopy, and on the second component we have our replacement. Can I erase these pictures? No. All that we need from these pictures is just this. So, now I can state finally some results. So theorem 1, every isotopy of a knot. Yes, let me also add to this definition that the linking number is 1, because I don't want to say this again every time. That the linking number is 1. So I'm assuming that the linking number between these components is 1 whenever I say about... No, this is not good. Well, okay. Every isotopy of a knot extends to a two-boardism between links with linking number 1. So I can always do a group of height 2. If I allow to do group of height 2, then I can always do this picture. Theorem 2.
Для любой второй компоненты, да? Заданной в конце изотопии.
Yes, it's true. Yes. This theorem doesn't say it, but it is true. Yes. There exists a link of linking number 0, which is not subordinate to any piecewise linear link, or to any smooth link if you want. So two-boardism is not such a stupid thing to do, at least if you do links of linking number 0. So for linking number 0, actually, there is a link. So the first component is wild, the second component is tame. And it is not.
Ну вы докажете теорему Рольсона из этих двух теорем.
If the linking number was 1, then I would solve Rolson's problem. But unfortunately, the linking number is 0.
А у вас там в одной теореме 1 стоит, а в другом 2, и в этом... А вы там 0 не можете поставить?
No. I cannot put 1 here and I cannot put 0 here.
Если бы числа сцепления совпадали...
Yes, then the Rolson's problem would be solved by these two theorems. Well, okay, it's not exactly, but at least it would be almost solved. Okay. Theorem 3. There exists an isotopy from the unknown to itself, which does not extend to any three-boardism of links with linking number 1. And actually, I can replace 3 by 2.5. So let me explain what is n-boardism for half integer n. So for half integer n, if we look at the geometric picture, well, here there are two dual cycles, and so if I let me define growth of height 1.5. Вот я это сейчас объясню.
25 или 2,5?
2,5. Okay, this is talk in English, so I should put dot. What is a group of height 1.5? Or yeah, maybe here I can explain it. So this means that I'm choosing a half of this basis and I'm attaching. No, this is not drawn well. It should be like this. I'm attaching a surface to just a half of the basis. So I'm attaching a surface here and a surface here, but I'm not attaching any surface to these two loops. And the group of height 2.5 is the following. Here I'm attaching surfaces to both generators, to this and this and this and this, all four. But on the next stage, I'm attaching surfaces only to half of the generators and not to another half. To another half I don't attach.
Вы там 3 сначала поставили. Было...
Yes, both statements are true. Because this is stronger than 3. 2.5 is stronger.
Понятно, но это нужно еще понять. Да. Ну так 3 было бы это самое популярнее, я бы так сказал. 2,5 это уже нужно.
But 2.5 is more interesting.
А продолжать можно вот там 2 и 3 четверти?
Можно. The extension is I have only 2.4 Borgism, but I don't know for other. This I know, but only this. I can define, yes, 2.4, yes.
А как это может быть не дробь с знаменателем степени двойки?
Well, it can be called 2.5 minus epsilon. Maybe this is better.
Уже понятно.
Тогда ведь сейчас. Тогда ведь точная, это же получается точная граница. Или вы имеете в виду, что конкретно эпсилон?
No. It's just something between 2 and 2.5. I don't know how to call it. And let me state theorem 4. I think I have to erase something. Okay.
Вы сами базис можете выбирать, как вам нравится, половинный, да? Или у вас нет такого выбора?
Yes, you can choose which half of the basis, but it is not important because you can exchange these two cycles by homeomorphism. So this is a separate handle. Each handle is separate, and for each handle there is a homeomorphism of a punctured torus which changes meridian and longitude. Theorem 4, the Bing's link is not isotopic to the unknown. By any isotopy which extends to a 2.5 Borgism of links with link number 1. So this is similar to theorem 2, but now I do have linking number 1, but instead of 2 Borgism, unfortunately I have 2.5 Borgism. And this is because coherence invariants behave differently for links of linking number 0 and links of linking number 1. Both theorem 2 and theorem 4 are based on coherence invariants. But for links of linking number 1, they give only 2.5 Borgism, and for links of linking number 0, they give 2 Borgism. This is a fact of life.
То есть единственное, что здесь неизвестно, это возможно ли там двойка, да?
Unfortunately, it's
А,
not
теорема
possible.
1.
It is not possible, yes. Yes, because of theorem 1. Because of theorem 1 and some examples.
Может, какой получше, чем Слинг-Гинка кандидат? Он бы это самое...
Maybe. You are free to invent.
Ну да, вот сейчас я решу.
So everything is going on between 2 and 2.5, and so there is still some hope that you can find some intermediate relation like 2.3 Bourdism, so that you can prove this theorem to hold for 2.3 Bourdism, and also you can prove this theorem for 2.3 Bourdism, and then Rolfson's problem will be solved. But also I think it is important to check the examples, namely, so what is the examples? This theorem 3 is the main example. If, for example, this theorem 3 is false and the opposite statement is true, then also Rolfson's problem will be solved. If, for example, I made a mistake in the proof of theorem 3, and you can prove that theorem, the opposite theorem, so every isotopy extends to 2.5 Bourdism, then Rolfson's problem will be solved. So I think it is important to check theorem 3.
Нет, ну ошибок, наверное, нету, не надо про ошибки. А вот скажите, вы все это можете переформатировать в квазиизотопию и делать по вашим этим самым инвариантам квазиизотопии, что более понятно лично мне, чем...
The proofs of theorem 2 and theorem 4, they depend on n quasi-isotopy.
То есть внутри.
Внутри.
Нет, а может нельзя ли формулировки сделать на языке квазиизотопии? Ну понятно, что может вам это не очень нужно, но принципиально. Это вот...
You see, n quasi-isotopy is something stronger than link homotopy. And here I am doing something weaker than link homotopy. Because I am just exchanging component, replacing it.
Нет, просто ваша философия очень понятная. Вы наводите узел на резкость, и потом, ну вот как вы двухкомпонентные делаете, так и однокомпонентные. Но у вас там более сложные инварианты, которые вы еще как бы один квазиизотопий, два квазиизотопия. В философском плане тут все прозрачно. А здесь вы новую теорию, значит, представили, и нельзя понять, значит, тут, конечно...
So if you look at the proofs of theorem 2 and theorem 4, of course the idea is to approximate this wild isotopy by something tame, by piecewise linear, and this approximation involves n quasi-isotopy. So really here, instead of isotopy, you have an n quasi-isotopy, geometrically. But here, I don't see how you can use n quasi-isotopy.
В общем, пока неизвестно. Ответ, что пока не получается внутри теорем только рабочий инструмент квазиизотопии. Просто когда вы для двух компонентов формулировали идею, то у вас не было этих группов, и поэтому как-то было понятно. Вы там красивые эти самые цепные дроби там вписывали, все такое. Вот, а здесь другая техника, да, для однокомпонентного.
These groups are needed just to state results. They are not needed for proofs. They are needed for statements.
Нет, но у вас она еще не решена, проблема. Может быть, что это...
Yes.
Поэтому эти statements, они пока что имеют статус промежуточный.
Maybe you can, instead of groups, maybe you can try to do something else here. But I don't have other ideas. I think it is natural, because it is sun filtration is a fundamental group, and it also has geometric meaning. If you do lower central series here, it is not interesting. It is interesting to do derived series here. So, if we are not very tired, I hope still to prove theorem 1 and theorem 3 after the break, or maybe at least something. What? Perhaps now it's time for break?
Не, ну это можете, да, никто не запретит. Я хочу сказать, что в следующий раз можно, наверное, продолжить. А вот через раз я буду отсутствовать, если вы хотите продолжать. Третий раз нужно прерваться. Или вы не хотите прерваться третий раз?
Okay, another opportunity is just to finish for today and continue next Monday.
Next Monday,
Theorem 1 and theorem 3. As you say, I'm ready to continue. So theorem 1 is actually easy. Theorem 3 takes some work.
Мы сколько? 2,5 часа уже сидим или сколько? Нет, 2,5 не сидим. Всего лишь 2 часа и 19 минут. Ну, а хотя вы раньше начали, можно сказать, что память, ну, 2,5 часа, да.
I started on time, not early. Well, actually there are 3 different proofs of theorem 1. One proof is group theoretic, another proof is module theoretic, and the third proof is geometric. The reason why there are 3 different proofs is because I could not believe for a long time that this theorem is true, and just by looking at one proof it was not enough for me. Especially if you have an algebraic proof, you still feel it that you don't understand everything, because okay, there is a proof, but how?
Лично, если вы спрашиваете мое мнение, то в следующий раз вам лучше продолжать. Вы можете после перерыва что-нибудь рассказать, но не то, что вы сейчас анонсируете, 8 доказательств первой теоремы, это не нужен просто перерыв. Вот. Но это самое, а потом я могу это самое продолжить. Мне там это самое нужно тоже продолжить. Но это только на 4-й раз я могу. Раньше никак не могу. Вот. Ну так что в следующий раз вы все продолжите, а после перерыва расскажите, что хотите, а кто хочет, тот уйдет, если не сможет. Все равно потом повторять будете.
So, what do you suggest? We continue today after the break, yes?
Не, ну я не возражаю.
Okay.
Я просто предлагаю в следующий раз все вот с этого места еще раз повторить.
Andreas, how about you? Are you okay to continue after break?
I'm okay. I must say, if this goes longer than 7 p.m., according to my time, or 9 p.m. according to your time, then I will lose the chance to get a warm meal today.
So, I think we can have a break for about 20 minutes, and then in about 1 hour we can discuss 2 proofs of theorem 1. Yes. Is it okay?
If you do it, I will listen.
All right.
I will try to listen.
All right. So for theorem 3, I think we have to postpone it.
Okay. Sergey, allow me another question.
Yes.
So, what is the precise definition of this two-board distance? So the main question for me is, okay, for the standard definition of boardism, you have one main boundary. And then the homology basis consists only, or may consist only of these canonical curves that you have in the Handel picture. If you have your picture, then you have 2 boundaries. And the canonical homology basis would also involve one boundary parallel curve. Does one need to find a spanning disk, therefore, or not?
For boundary parallel curve like this one?
Okay, in the main picture you always had 2 different boundaries.
Yes. You mean
So,
you mean this and this?
No, but in the application, I think that, so in EG, I cannot point. Yeah, or the picture left to it, then you have an upper boundary and a lower boundary.
This and this? this and this? Yes?
I don't understand really the pictures, but usually then you had two boundaries. The thing, and you are spanning two knots.
Okay.
You want to have
Okay, I see.
Knots. You have two boundaries.
I see what you mean. I see what you mean. Yes, this two knot. When I replace one knot with another, yes. So they are supposed to co-bound the group. So like their connected sum is supposed to bound a group. Yes.
Yeah, and then is the question. So you have then the surface which has two boundary components. And according to the ordinary definition of a homology basis, you need one generator more. The first boundary doesn't increase the number of generators with respect to the closed surface. But the second boundary does it increase. And is this additional generator to be spent?
Okay, I think I understand. So at some point I tried to use a different definition using groups with two boundary components. So here all groups have one boundary component. But now
and I want to know this definition.
Yes, but now I'm not using this definition. I'm only using definition of groups with one boundary component because, as you rightly noticed, there are some problems with groups with two boundary components. It's more difficult to deal with them. So I'm not using them. I'm only using groups which have one boundary component. And here, to say this in geometric language, so algebraically, this definition of n-bordism is that we just replace one component with another, provided that their classes are conjugate modulo the nth term of the derived series. Now this conjugate corresponds geometrically to taking their connected sum. So conjugate means that we have two tails and then some additional element here which effectively makes just this tails longer. So we go like this. So conjugation corresponds to choosing some path from one component to another. And then we go from one component to another, go around this component and then go back. So if you just shift this, you get a connected sum. It is not important, the shifting is not important because self-intersections are allowed here. We are just looking at the classes in the fundamental group, and so it doesn't matter which way we do the shifting. And so the question is it possible to take, so these two components, this replacement is good if there exists a connected sum of these two components which bounds a group of height n. Okay?
Okay. I think I need to go to the bathroom for the rest of the break.
Okay.
But I'll be back.
We can make the break longer, 30 minutes. Is it? Well, all right. So let's make the break. Yes.
How long is the break?
Если они готовы,
Я не слышал, спрашивали, но я
Если
просто
они берешь связанную сумму и смотришь, есть ли гроб заданной высоты. Но
элемент принадлежит энтому коммутатору, если ограничивает гроб,
он просто повторяет.
Но здесь вы пишете, что эти элементы сопряжены, то есть что они должны с обеих сторон доброситься на
вот в этой степени.
Как бы
Геометрически это означает,
они сопряжены при
что
помощи,
или
как я понимаю,
связанные суммы.
Да, вот это то, что я здесь пытался рисовать. Но мы, значит, должны как-то зафиксировать им хвостики и сопряжены, значит, что существует еще одна петля, вот, которая, собственно, их сопрягает. Но тогда что значит это сопряжение? Значит, что вот этот, скажем, равен фундаментальной группе вот такому. Сначала мы идем сюда, потом мы идем сюда, и потом мы снова... Нет. Сначала мы идем сюда, потом мы проходим вот эту, потом мы это проходим в обратном направлении.
Вы сопряженную петлю рисуете?
Да. Ну, значит, вот я иду сначала так, потом прохожу вот эту, а потом прохожу, а потом, значит, возвращаюсь, прохожу ее же вот рядышком я рисую в обратном направлении. И что-то я тут опять запутался. Ну, в общем, короче говоря, вот это вот рядышком, это как раз соответствует просто связанной сумме. Но можно это подробнее нарисовать.
А вот почему мы хотим, чтобы вот прохождение вот этой подряд было коммутатором чего-то? Это как-то можно объяснить?
Ну, тенбортизм так определяется. Он в доказательстве будет использоваться.
Ну, просто мы хотим как бы изменить эту компоненту не слишком сильно. Ну а что значит не слишком сильно? Должна быть мера какая-то не слишком сильности. Ну вот мера, что они сопряжены по модулю n-того коммутанта.
Вот, то есть получается, значит, мы хотим, чтобы прохождение их подряд было элементом, получается, первого коммутанта.
Нет, как раз таки n-того коммутанта. Потому что даже что значит, что они сопряжены по модулю n-того коммутанта? Это значит, что, ну давайте я напишу А и Б. Да, это значит, что А равно B в степени G по модулю этого, значит, этого коммутанта. Но это, значит, можно написать так, что А минус 1, B в степени G принадлежит этого коммутанту. А вот это вот и есть, значит, соединен, вот связанная сумма.
Да, я перепутал по модулю. То есть, значит, отличается на элемент из сейчас G у нас. G откуда?
G это вот это фундаментальная группа дополнения вот к этому. Вот мы все смотрим фундаментальная группа дополнения вот к этому.
Тогда про прохождение двух этих петель просто подряд. Что верно?
Но что значит подряд? Мы не знаем, каким образом подряд, потому что здесь есть вот эта самая петля G. Ну то есть вот связанная сумма, она просто может быть разная. Да, вот такая, а может быть такая.
Про нее не было никакого утверждения?
У меня было утверждение. Ну, то есть геометрическое определение анбордизма такое, что мы имеем право заменить одну компоненту на другую, если какая-то их связанная сумма ограничивает гроб высоты n.
Связанная сумма при помощи G.
Ну да.
Понял, спасибо.
Из неонов есть делители нуля, но вот неонов нет.
Постойте, пожалуйста. Я про эти теоремы хотел попросить все-таки назвать все комбинации, которые вот могли подать решение проблемы Ролсона, если бы что-то было не так. Вот одному сказали, что если бы коэффициент зацепления был одинаковый, еще если бы вот здесь была двойка в совокупности с первым фактом, а вот третья теорема, она как-то так включается.
Ну, если бы вот здесь было 2,5, то получилось.
Ну вот если бы эти два числа были равны.
Да, если бы эти два числа были равны.
Если бы два числа были равны,
в принципе, остается надежда, что это можно увеличить, а это уменьшить. Но на самом деле, если оно увеличится так, что эта теорема будет верна в такой форме, то это значит плохо. То есть это слишком много доказали. Потому что там есть такой пример, который такие все увеличения, он В общем, он говорит, что это значит, что слишком много доказали. Но если в более слабом смысле увеличить не всякую нет, хорошо, это нормально, это нормально. А вот тот вариант, который вы сказали, что вторая компонента фиксирована, да, и вот с любыми заданными вторыми компонентами, если такой бардизм есть, то уже плохое утверждение, оно как бы слишком много доказывает. И если его удастся доказать для какого-то промежуточного бардизма, то это значит, что дела плохи. Ну, то есть это значит, что такая, тогда не докажешься для этого промежуточного бардизма. А если вот именно в таком виде это усилить, а это тоже усилить, но в смысле здесь уменьшить, а здесь увеличить, то тогда может получиться теоретически, да. Но проблема в том, что как бы моей техники уже здесь не хватает с полиномом Александера. И дальше, чтобы вот что-то такое делать, ну, видимо, нужны какие-то высшие полиномы Александера. Ну, видимо, там полином Джонса. В общем, тут
полином Александера двухпеременных нужен.
Я его использовал. Мне кажется, что я из него уже вытащил все, что можно было вытащить. Ну, конечно, значит, есть еще полином Александера.
Это надо Манторову рассказать. Мы тут не можем ничего.
Нет, вот Фунар разбирается в полиноме Джонса, хорошо.
Что он нам расскажет, мы тогда тоже будем разбираться. Пока что
он текст написал.
Никто не разбирается.
Ну, в принципе, есть еще полином Александера от трех переменных. И есть, ну, вы попробуйте ставить две компоненты.
Вот это интереснее.
Ну, вот, может, у вас получится, но я не придумал, как туда две компоненты ставить, как-то это.
Ну, просто полином Джонса, он совсем другие задачи решает. Если вы еще хотите его применить, это вам нужно нам все с самого начала будет рассказывать.
Нет, ну, понимаете, бывают же эти аналогии Иошуа Тезаба, которые обобщают тоже полином Александера. В общем, тут, конечно, при желании можно это, значит, дальше развивать, но я, видимо, уже готов остановиться и переключиться на что-то другое. Но вот мне кажется, сейчас, значит, надо это сказать, чтобы не потерялось, потому что кое-что все-таки я тут получил. Вот.
Ну, вы, конечно, можете остановиться и переключиться на что-то другое, но вам придется нас останавливать.
Нет, я вот хочу сказать, пока это не забылось, но вот.
Да. Ну, давайте. Только я через час точно уйду. Вы сказали, что через час. Если вы через час не докажете, то шансов у вас заставить меня это слушать.
Ровно 8.
Нет, я обещал быть 9 дома, но это полное вранье. Но если я еще полдесятого отсюда уйду, тогда уже совсем будет вранье в квадрате. Давайте за час что-нибудь расскажите.
Да.
И...
Хорошо, Миш, вопрос?
Я потом задам после 9.